Before we move on to looking at the point of intersection of two tangents or two normals to a parabola, I want to define three quantities, two of which we will use quite a lot, one much less so. So the first one is the notion of a focal chord. So a chord is any line segment that passes between 2 points on the parabola, but if that line segment also passes through the focus, the point A, 0, it's called a focal chord. Secondly, the x-axis is clearly a line of symmetry for the parabola, and that is just called the axis of the parabola. And finally, if we take a focal chord but which is vertical, so perpendicular to the axis, then we can work out what the length of that is, and its name is called the latus rectum. In order to work out its length, we can clearly work out the y coordinate when x is equal to a, which from the equation of the parabola gives us that will either be plus 2a or minus 2a. In other words, the length of this line segment is 4a, and that's called the latus rectum, and a half of that is called the semilatus rectum. In other words, 2a, just the length from the focus to this point here. So how do we determine the point of intersection, or the coordinates of the point of intersection of two tangents to the parabola? Well, let's suppose that we have 2 points on the parabola that are distinct, labelled as AP squared 2AP, AQ squared 2AQ, where P and Q represent the parameter for those 2 points. And let's suppose that R of x, y are the coordinates of that point of intersection. Now, first of all, because the tangent at the point AP squared 2AP has the form given by equation 1, and similarly the equation of the tangent at AQ squared 2AQ is given by equation 2, because capital X, capital Y is the point of intersection of those, capital X, capital Y lies on that, each of those tangents. In other words, x, y satisfies these two equations. So 1 and 2 merely represent the fact that capital X, y lies on both tangents. Now, if we take these two equations, because we're after finding explicitly what x and y are, we can subtract them to eliminate, in this case, x. It doesn't matter how you eliminate x and y to find each in terms of p and q, but this is one easy way of doing it. So if we subtract these two, we get equation 3, and then noticing that p squared minus q squared is a difference of two squares which can be factorised, then equation 3 becomes equation 4. I've merely replaced p minus q by minus q minus p, and then notice that the whole equation has q minus p as a common factor. So in equation 5, which only has y and then p and q in it, if we divide through by q minus p or p minus q, which, assuming p and q are two different points, then the parameters for those 2 points will be different. Then we end up on rearrangement having divided through by q minus p, equation 6. So going back to these two equations, which represent the fact that x, y lies on those two tangents at p and q, on elimination we find that y is given by this expression, a times p plus q. Now, if we substitute for that value of y into either of the previous two expressions for the tangents, let's suppose we take this one, we can then end up with x given by this formula, which is very simple. It's just a times p times q. So from now on in, the two tangents at the 2 points p and q with parametric coordinates ap squared 2ap aq squared 2aq are x equal apq, y equal a into p plus q. Now there's another subtle way of determining that point. So here goes. Let's suppose that we take hk in the plane and draw from it to the parabola the two tangents, which will be tangents at, say, 2 points ap squared 2ap, aq squared 2aq. Now obviously if we could determine hk in terms of p and q, then we would have determined the coordinates of the point of intersection of those two tangents. So to begin with, any tangent at a point at squared 2at will have a Cartesian equation given by this form here, where x comma y represents any point on that tangent. Now by substituting into this equation for the tangent at some general point on the parabola the two coordinates h comma k, we end up with this expression, and this just represents the fact that at at squared 2at the tangent passes through h comma k. However, we can interpret this equation in a different way. We can look at that and say that for given h and k, this represents a quadratic in t, where t would represent the parameter of the 2 points for the two tangents to the parabola, which can be drawn from h comma k, i.e. the two tangents that meet at h comma k. So taking this expression here as a quadratic and interpreting it in that way, let's suppose that the two tangents that pass through hk are tangents at 2 points with parameters p and q. They represent the roots of this quadratic. Now we already know that the sum of the roots of this quadratic, which will now be p plus q for the two parameters, will be the coefficient of t, which is k, divided by the coefficient of t squared with a minus sign. So this is the standard expression for the sum of the roots of a quadratic being minus the coefficient of the linear term, so that will be plus k, divided by the coefficient of the quadratic term. Similarly, the product of the roots of this equation, and the two roots we're assuming are p and q, will be the constant term divided by the coefficient of t squared, so h over a. Therefore, if from hk we draw two tangents to the parabola, and they are at points ap squared 2ap, aq squared 2aq, by interpreting the roots of this quadratic equation as p and q and writing down the formula for the sum and the product, we find that h and k on rearrangement are apq, ap plus q. In other words, those are the coordinates of the point of intersection of the two tangents at those 2 points.